So you like go to the grocery store and you like walk down the aisle and you see both ends on your on the grocery stores. You have boxes and boxes of all this delicious food and stuff like that. And you notice that some of them claim to say, I don't have trans fats, I'm healthier. Oh, I have more unsaturated fat, so it's got to be healthier. But what does all these mean? And how do I know why is it healthier for me? I mean, am I just going to take some doctor or someone who claims to be a TB doctor or a health expert to tell us why some fats are healthy and some fats are not, or just like don't have no fats at all, and you get to lead a healthier lifestyle without understanding the chemical properties? No. You're going to find out why fats are good or why fats are not so very good. Here we go. So before we go down to talk about oils and fats, you got to understand that they are basically the same thing. All right? They are just triglycerides. Now, fats and oils, even though it's in the polymer section of your syllabus, it's not really a polymer. All right? It's a long chain molecule, but it's not a polymer. So what are triglycerides made of? Or what are oils and fats made of? Well, oils and fats are made of a long carboxylic acid chain. All right? A long carboxylic acid chain. Notice that I have written N here to note that it's a really, really, really long chain. All right? So you need for every fat triglyceride to form, you need 3 carboxylic acids. And now these carboxylic acids are also called fatty acids. Fatty acids. So you have 3 fatty acids reacting with 1 glycerol in a condensation reaction, and what you make is a triglyceride. So again, what you have is a loss of 3 water molecules. The water molecules is going to come from the OH of the carboxylic acid. Just like how we talked about the condensation reactions for all the other polymers and natural macromolecules in previous units. So loss of water molecule and you get a triglyceride. So you have a long hydrocarbon chain with this ester chain right here. Okay? Now, this is something interesting. Because of the long hydrocarbon chain here, fats tend to be hydrophobic. But in this region, where it has oxygen in there, it tends to be slightly more hydrophilic than the rest of the chain. This makes triglycerides to be great products, like making emulsifiers when you combine it with long hydrocarbon molecules with water molecules. All right? So now let's talk about why some fats are good and some fats are not so good. Now remember, oils and fats are the same thing again. But what makes an oil and fat and fat? Well, it all has to boil down to the length of the hydrocarbon chain, the hydrophobic carbon chain, and the composition of that long chain. So when we hear health professionals talk about saturated fats and say, yo, you got to reduce your consumption of animal fats because animal fats are saturated fats and that's really bad for you. So what are those? Well, here I have a small little diagram of a saturated fat. Okay, here we go. Saturated fat is a long chain. It could be longer than this. I'm just sketching it out. It's not completely accurate, but the concept is the same. A long hydrocarbon chain and this ester linkage over here. All right? So remember in the alkane units, I talked about long hydrocarbon saturated carbon chains being viscous or solid at room temperature. And for oils and fats is basically the same thing. Now, the longer the chain is, and if it's a long linear-like chain, like what I've drawn here, and it's all saturated, that means its melting point is going to be pretty darn high. And when you consume saturated fats, it may solidify in your bloodstream, cause your arteries to clog up, and you may like, you got fat all over your blood flowing in, your cholesterol levels will go high, your blood pressure will go high, and it's not really good because now your heart has to do more work to pump blood through your arteries and all that stuff, so it's not really good. So what can you do about saturated fats? Well, your body still needs saturated fats, by the way, but in moderate proportions. But generally speaking, it is healthier to have fats that are slightly more unsaturated. What does unsaturated mean? Remember, in the alkenes unit, we talked about unsaturated hydrocarbon chains, right? So if I say unsaturated, I will basically add a double bond somewhere along this long chain. So I'm just going to add double bonds anywhere. It doesn't really matter. In nature, these double bonds may be at a fixed position, but I'm just going to illustrate what I've drawn here. And if you notice, I've drawn the double bonds, but I haven't really affected the shape of this hydrophobic chain. So what I've drawn here is basically a trans unsaturated chain, all right? A trans. What is a trans? A trans double bond is simply a double bond where the hydrocarbon long chain are on opposite sides of the CC double bond plane. All right, they're on opposite sides. So when you look at this, they are on opposite sides. It doesn't really change the shape of this triglyceride, and that's why trans fats, even though it's unsaturated, still come a little more useless. Yes, the melting point has decreased, but not so much, physically speaking, right? So what we need are fats that are unsaturated, but are not unsaturated. We need cis unsaturated double bonds. Now, cis double bonds are where the long hydrocarbon chain are on the same sides of the CC double bond plane. So when that happens, I technically will now have to redraw this long chain. Okay, stay still, board. Oh man, all right, here we go. Oh, now it hits. You notice that when I started drawing this, it's hitting like this chain here. So it's going to pop that chain, and it's going to move that chain, and it's going to like form weird odd shapes, and this chain is going to go down. And remember, this is also a double cis bond, and that is going to go down here, and this chain is going to look weird, and it's going to like go down here somewhere because this chain is kind of forcing it that way, and it's kind of trying to overlap each other and trying to find space in it, right? So that's exactly what is happening when you have a double bond on the same side. And I know it looks messy, but that's I'm trying to do my best here to draw proper cis double bond strain, but it's going to look messy. And so once you see cis double bonds being in place, this is the cis double bond, and it's facing the same side. This is another cis double bond, and it's facing the same side. This cis double bond is facing on the same side. And so you notice that your pink the long hydrocarbon chain. And when you kick the long hydrocarbon chain, you are essentially reducing its melting point. And that is why when you have vegetable fats that are polyunsaturated and also in cis double bonds, this will make vegetable fat become oils or liquid at room temperature. So that is why vegetable fats or vegetable oils are more favorable. But again, gotta take this in moderation because lots of it is also not very good. Now, it's quite important to note that when you cook vegetable oils, even though you're using it, but if you have it in high temperatures, you may change the structural isomer of the cis double bonds to trans double bonds. But that's a whole nother topic, and it goes much deeper than this elementary chemistry that we're talking about here. So now that you know what are saturated fats, monounsaturated fats, polyunsaturated fats, cis and trans-unsaturated fats, we can now talk about why fats and oils are essential. They are essential for us for certain metabolic processes in our bodies, but in general, more polyunsaturated fats that are cis double bonds, like olive oil, are healthier because it remains a liquid at room temperature and also when we consume it in our bodies. Saturated fats, like animal fats or palm oil, are not very good because they tend to be saturated and long and they will solidify. And you may ask me, Mr. Ko, then why is the cooking oil I buy at a grocery store, which is made out of palm oil, is liquid when I buy it? Well, that's because they add in additives into that oil. Natural palm oil, when it's freshly processed, will be liquid, but it will solidify over time. And I know it because I used to sell palm oil. All right. Anyway, so essentially, don't consume too much palm oil. Margarine now is a very interesting thing because we want to consume vegetable oils because it's healthier, but it makes it hard for us to spread oil on toast and stuff. So people will hydrogenate these unsaturated vegetable oils to have properties that look and feel and like butter, but has those same desirable health benefits of vegetable oils. Now that is not exactly true because you can't really have healthy saturated fats. Well, you should consume some of it, like I said, but in moderation. All right. So margarine basically has unsaturated and saturated fats, and then so it has both solid properties, but not so solid, so that you can spread them onto your toast. So finally, we ask, how do we extract these healthy vegetable oils? Well, the old-fashioned way is to press it. You get a nut or something, and you just pressing it, squashing it until you extract all this liquid out of it. All right. Another way is to centrifuge the whole sucker. You put the thing, you press it, and then you centrifuge it, and then you get some oily substance liquid that's out of it. But these oily substances are not pure, and what you need to do is to go through distillation of it. All right. So you put it into a reflux, and then condenser, and then turn up the sucker up, and then you basically boil out the oils and collect water in it as well, and then water on the bottom and the oil layer on top, and that's how you extract oils and fats from your nuts and vegetables and all meat, I guess. And, although people don't really do that, because